Now let's move on to our next presenter, Dr. A.S. Ashwinth Jeffrey. Are you here with us?
Is my screen visible, ma'am?
Yes, it is good. Yes.
Yes.
You can start.
Yes, ma'am. Greetings of the day, dear professors who are in the meeting. I am Ashwinth Jeffrey. I am a full-time math research scholar in the Department of Mathematics, Sri Sivasubramanian Order College of Engineering, Kalavakkam, Chennai, from India. So I'll be presenting my topic on influence of uncertain nanoparticle volume fractions on energy and mass transport in Maxwell Hybrid nanofluid flow under Electro-MHD-osmotic effects. So coming into the abstract, this research analyzes how uncertainty in nanoparticle volume fractions affects the energy and mass transport in the viscoelastic non-Newtonian Maxwell fluid flow over a shifting wedge. So in order to carry the study, the nanoparticles like Fe3O4 and TaO2 are considered in the present study, including the effects like electromagnetohydrodynamic, osmotic forces, thermoforces, Brownian motion, activation energy, and thermal radiation. So the volume fraction of nanoparticles plays a vital role in heat and mass transport, and that's why we have taken that volume fraction parameter as the fuzzy number and studied in terms of triangular and trapezoidal fuzzy numbers. And the fuzzy profiles of velocity, temperature, and concentrations were analyzed in the present study, and the triangular fuzzy number and trapezoidal fuzzy number were evaluated individually and observed that the trapezoidal fuzzy number effectively improved the accuracy and reliability of estimating the drag force, energy, and mass transport. And another key conclusion of the present study is that the hybrid nanofluid mixture emerged as the most thermally efficient, achieving an 8.15% heat transfer rate compared to the Fe3O4 blade, and 5.82% improvement over TaO2 blade, and 6.91% increase compared to the blade. So coming into the introduction, the single-phase heat transfer fluids like water, engine oil, ethylene glycol possess low thermal conductivity. So in order to improve this heat transferring performance and the thermophysical properties, the concept of nanofluid was introduced by Choi in 1995. So the nanoparticles like copper, gold, silver, nickel, aluminum oxide were used in the nanofluids. So the nanofluid consists of the nanometer size solid particles which are disposed into the base fluid, and the resulting mixture was seen to have higher thermal performance compared to the base fluid. And in order to improve this nanofluid, the concept of hybrid nanofluid was introduced by Suresh et al. In 2011, and it involves two different types of nanoparticles suspended into the base fluid with size under 100 nanometer. So they are widely used in uses coolants in heat exchangers, engine cooling, desalination, machining, refrigeration, solar collectors. So these hybrid nanofluid have enhanced thermal performance than base fluid as well as the nanofluid. So coming into the Maxwell fluid model, the mathematical Maxwell fluid model helps to investigate the relaxation behavior of non-Newtonian fluids. Thus, they can describe the viscous and elastic behavior of non-Newtonian fluids. The governing equations of the Maxwell fluid model is given below, and the methodology development. So I have given the definition for the membership function in definition 1, followed by the alpha ket of a fuzzy set in definition 2, and definition for a fuzzy set is set to a fuzzy number is given in the definition 3. And we have taken the volume fraction of the nanoparticle as the triangular fuzzy number and trapezoidal fuzzy number. Fuzzy number K1, K2, K3 is set to a triangular fuzzy number if the membership function is as given below in definition 5, and similarly that trapezoidal fuzzy number K1, K2, K3 and K4 is said to have a trapezoidal fuzzy number where the membership function is given by the membership function in definition 5. So coming into this governing equations, the first equation is the continuity equation, second equation is the momentum equation, followed by the energy and concentration equations in equations 3 and 4. These are the extensions from the Navier-Stokes equation. So we have considered the electro-osmosis effect, electromagnetohydrodynamic effect, thermal diffusivity, thermal radiation, heat source, Brownian motion and thermoforces, and activation energy effects in the present study. And the boundary conditions, before looking into the boundary conditions, as I have said, we have considered the fluid flow over the wedge geometry. So I have taken the wedge, having a wedge angle omega is equal to lambda pi. Here U and V are the velocity components along the x and y directions, And TW and CW are the temperature and concentration at the surface of the wall, and T infinity and C infinity are the temperature and concentration away from the wall. So the boundary conditions for the momentum, energy and concentration equations are given here for y is equal to 0, which means at the surface of the wall, and for y goes to infinity, which is away from the wall. And the table 1 describes the thermophysical properties of the nanoparticles and the base fluid. And with this table 1, we have calculated the thermophysical properties like viscosity, density, heat capacity, and thermal conductivity, along with the electrical conductivity of the hybrid nanofluid mixture. And introducing the dimensionless transformations. So we have used this dimensionless transformations as we can see that the governing equations are in the form of partial differential equations, which are in the dimensional form. And in order to reduce that dimensional equations into the non-dimensional ODE, we have used this similarity transformations. And using the similarity transformations, we have reduced this partial differential equations into the ordinary differential equations. So equation 5, 6, and 7 are the momentum, energy, and concentration equations, along with the reduced boundary conditions shown in the given equation 8. And the key engineering parameters like the drag force, the energy transmission rate, and the mass transport are calculated numerically and represented here. And coming into the numerical analysis, we have solved this coupled ordinary differential equations using the shooting technique in MATLAB. So this we introduce these variables to reduce the boundary value problem to an ordinary differential equations of first order. And the present numerical simulation is validated with the existing research of Sulkarnain and Shanmugapriya, shown in the research articles 7 and 8. And the present results were tabulated in the table 2 and 3. And coming into the fussification, so we have used the alpha cut technique to convert this ordinary differential equations into the fussy differential equations. So the equation 11, 12, and 13 shows the fussy differential equations of momentum, energy, and concentration with the reduced conditions in equation 14. And the table 4 describes the fussy values of the nanoparticle volume fraction. As I have said, we have considered that as an uncertainty parameter. We have taken 3 values for triangular fuzzy number and 4 values for the trapezoidal fuzzy numbers. And coming into the numerical results, with the non-dimensional parameters like magnetic field parameter, electric parameter, Smoluchowski velocity parameter, electro-osmosis parameter, Deborah number, electro-osmosis parameter affecting the skin friction, and similarly these parameters are radiation parameter, Eckert number, so heat source parameter and Prandtl number affecting the Nusselt number, and the Lewis number, chemical reaction parameter, thermophoresis and Brownian force parameter affecting the mass transport are analyzed numerically. And coming into the fuzzy results, and in the fuzzy velocity profile, we can see that the hybrid nanofluid mixture shown enhanced drag force compared to the fluid containing a single nanoparticle, which means Fe3O4 in the presence of blood for eta is equal to 1, 2, and 3 in the cases of triangular and trapezoidal fuzzy numbers. Similarly, while we are considering the fuzzy temperature profile, the hybrid nanofluid mixture shown enhanced performance than the nanofluid mixture for eta is equal to 1, 2, and 3 for both the cases of triangular and trapezoidal fuzzy numbers. Similarly, for the concentration profile, we have seen that we can able to see that the hybrid nanofluid mixture shown enhanced concentration profile than the nanofluid profile for triangular and trapezoidal fuzzy numbers. And we have checked the performance analysis of both the triangular and trapezoidal fuzzy numbers for in the respective profiles of velocity, temperature, and concentration for different eta is equal to 1, 2, and 3 in both the cases of hybrid and nanofluid case. We can see that from the table that the trapezoidal fuzzy numbers is having lesser mean values compared to that of the triangular fuzzy number, and the heat transfer computation is analyzed, and it can be found that
Sorry, sir. You have 2 minutes left.
Yes, sir. Yes, ma'am.
With your paper, thank
Yes,
you.
ma'am. The key finding of the present study is that the hybrid nanofluid mixture shown 8.15% enhanced energy transmission rate than the mixture containing Fe3O4 blood, and 5.82% energy transmission rate than TiO2 blood, and 6.9% energy transmission rate than the blood. So coming into the conclusion, the electric parameter and magnetic field parameter and electro-MHD forces shown increasing pattern in F double dash of 0. 0, and the electro-osmosis parameter, Smolotowski velocity parameter, electric field parameter increases skin friction drag, and the heat source parameter, Eckert number, thermophoresis, and Brownian motion parameters significantly contribute the enhancement of heat transfer profiles. And as we have seen now, the hybrid nanofluid mixture shown enhanced profiles in fuzzy velocity, temperature, and concentration profiles compared to the nanofluid case. The hybrid nanofluid mixture demonstrates superior thermal performance than 8.15% energy transmission rate than Fe3O4 in the presence of lead, and 5.82% increase over TiO2 in the presence of lead, and 6.91% than the base fluid blade. The trapezoidal fuzzy number provides more stable and conservative estimations than the triangular fuzzy number for hybrid nanofluids. It enhances the prediction for heat and mass transport, making it a reliable method for analyzing the Fe3O4 and TiO2 mixture in the presence of lead. So I have shared this references of the present study.
Thanks a lot, Dr. Jeffrey, for your presentation.
Thank you, sir.
So if there is some remark, we can contribute from the other chair.
Yes,
Dr. Sundareswaran.
Thank you very much for your great presentation. Yes, sure. Dr. Burumi,
Yes.
two participants had questions about previous article. Dr. Sandar?
Sundareswaran.
Yes. Please go ahead and feel free to ask your question.
Ashwin, is it audible?
Yes,
Yes.
ma'am. Yes, ma'am. It's audible.
I have one question.
Yes, ma'am.
What is the advantage of applying this fossilization in heat transfer problem?
Ma'am, volume fraction parameter, actually the volume fraction parameters plays a vital role in a heat and mass transfer. Actually, this heat and mass transfer is the most efficient factor in industries and applications in industrial industries, which has a major role in coolants and automobiles. So this volume fraction parameters usually in our present study we used to vary from 0 to 0.2 range. So while we are taking the percentage of nanoparticles, the percentage of energy transmission rate varies from different ranges. So there is an uncertainty developed there. So in order to understand this, we have taken it as a fuzzy number and studied in terms of triangular and trapezoidal fuzzy numbers, ma'am.
Okay, good.
Myself, I'm Shanmugapriya Roy Chaudhary.
Yes.
So I just wanted to know whether do you think that fuzzification was much needed for this problem, because fuzzy is typically used for evaluating the vagueness. So where do you think the vagueness is actually there in your study, and why do you think that only fuzzy can justify the outcome? And have you thought about validating it through more generalized fuzzy sets or not?
Usually this volume fraction parameters affects these both. In our present study, we have the numerical equations, momentum equation, energy equation, as well as the concentration equation. So coming into this, I'll show this. So these are the reduced equations, ma'am. Equation 5, 6, and 7. So when we are looking into this A1, A2, A1, A3, this A1, A2, A1, A3, A3, A5. So these are all the constant. Sir?
Your screen is not visible.
Not visible.
Show your slides.
Yes. Oh, sorry, sir. Is it visible, sir?
Yes.
So when I have shown this slide. So equation 5, 6, 7 are the reduced ordinary differential equations. So coming into this equations, this A1, A2, and A1, A3, and the constants like A1, A5. These are all the dimensionless constants. This all A1, A2, A3, and A4, A5 terms contains the volume fraction parameters. So this all volume fraction parameters affects all these equations, this momentum equation, this energy equation, as well as the concentration equations, since they are coupled equations. So if there is a change in the equation 7, it also affects the equation 6. Also, if there is an change in an equation 6, it affects the equation 7. So the volume fraction parameters simultaneously affect all these 3 equations, and that's why we have taken this fuzzy differential equations using this AlphaGet technique, ma'am.
Good. Thanks, Jeffrey, for the clarity of your explanation. Thanks a lot.
Thank you, sir.
You can move. Now we can move to other articles for contribution.
Yes, sure. Thank you very much.